So we move on to example number 9. So the question reads, a uniform 100 Newton pipe is used as a lever as shown in figure 9. Find the magnitude of the torques about the pivot if a 500 Newton weight at one end is balanced by a 200 Newton weight at the other end. So in this particular case, we are being simply asked to find out what the torques are. Okay? It says find the magnitude of the torques. Find the magnitude of the torques if about the pivot if a 500 Newton weight at one end is balanced by a weight of 200 Newtons at the other end. So basically in this case, in a setup like this, the pivot turns out to be the knife edge on which this particular thing is being balanced, in which this particular pipe is being balanced, which is what we have there. There is a weight this side, which is 200 Newton. There is a weight this side, which is a 500 Newton weight. So there is a weight at the end of the pipe, this side, 500 Newtons. There is a weight at the end of the other side, which is 200 Newtons. And of course, this pipe has got a weight. We have been told the weight of the pipe is 100 Newtons. Now, if you have got if an object has got a weight, like in this case a pipe, the weight of that pipe acts through the center of mass or the center of gravity, which happens to be right through the center of the pipe, which is the 1,000, which is 100 Newton we are seeing here. Of course, there are other forces. All these forces, the 200 Newton force, the 500 Newton force, the 200 Newton weight, Newton force, the 100 Newton weight, and this 500 Newton force are all trying to drag the pipe down. That's what these forces are basically trying to do. They are trying to drag the weight of this particular thing down. However, since this particular thing we've been told remains balanced, is balanced, so it doesn't accelerate downwards, there is a force which is being provided by this knife edge. And usually knife edges tend to provide a force which is a reaction force which is in the opposite direction to what these other forces are doing. So you've got a force being generated by a knife edge which is trying to push this pipe up, and that's a force which is indicated by this arrow here. We call that a reaction force. Are we clear? There has to be a good understanding of what's happening. The pipe has got a weight which is 100 Newtons. The weight of the pipe is going to act through the center of the pipe, which is what you have here. Then there is a 500 Newton force this side on one end. There is another 200 Newton force on this other end. Then of course, all these forces, what they're trying to do, the 200, the 100 Newton force, the 500, they're trying to pull this pipe down. But it's not happening because the pipe is balanced. The reason why the pipe remains balanced is because why it doesn't move downward is because this particular knife edge which you have here is pushing against the pipe upwards through this force, FR. Are we clear?
Yes, sir.
Okay. So with that out of the way, the next thing item is you can choose the length of the pipe. The length of the pipe you have not been told, because it's not really necessary to know what the length of the pipe is. So we can just say fine, the length of the pipe is going to be L. Now you can choose where you want to measure the length of the pipe from. If you want to measure it from this side, say from this side to here, that is X, then the remaining side from this side to that side, that's going to be L minus X. Or you can choose to say you start from this side, this is going to be LX, then this other side is going to be L minus X. So that choice is yours. We leave that to you to choose where you're going to measure from this side up to here. How much is the length? If you call it X, because the whole length is L. So if from this end to this particular end here, calling it x, then the remaining length is supposed to be L minus x. Are we clear? Are we clear?
Yes, sir.
Yeah. We have to do this because we're trying to work out torque. We need to know the distance from the pivot. If this is our pivot here, then from the pivot to the point where the force is being applied, that distance needs to be known. That's why we are interested in saying from here to there, let us call it x. If from here to there we're calling it x, then the whole bar has got the length of L, then this other side is going to be L minus x. So with this L minus x here, we know the length from the pivot to the point of action of this force, the 500 Newton force. So we need the force, we need to know the distance. The distance is L minus x. Okay, then of course we know the angle. Then there is this other force here. This force here is 200 newtons. So if you're calling this whole thing from here to there as as x, then we can work out the torque being produced by this particular guy. But there's also this guy here. There is also this. Now, the distance from here to there is x, but the distance from here to here is L divided by 2. So the difference between here and there, from the pivot to this point, it's going to be x minus L divided by 2. This distance from here to here. If the distance from here to there is x, and the distance from here to here is L minus 2, then the remaining distance here is going to be x minus L minus 2, x minus L divided by 2, this distance. We need to know the distances from the pivots to the point of action of the force for us to be able to work out torques. Are we clear? So mark this distance. Remember, I asked people to print these notes. So the distance from here to here, mark it as x minus L divided by 2. We need to know the distances. And of course, this particular one, the reaction force, this reaction force, as you can see, it is acting through the pivot. So if a force, the line of action of a force is acting through the pivot, then that particular force will not produce any torque. So there will be no torque produced by this force FR, the reaction force. The only torques will be produced by the 200 Newton force, the 100 Newton weight, and the 500 Newton force on this particular side. Are we clear? Is it clear?
No, sir.
This particular weight this side will be trying to turn the beam this side. This weight this side will be trying to turn this bar, this pipe this side. So that's going to be a clockwise torque. So this one will produce clockwise. This one here will be trying to turn the weight, the bar this side. So that's going to be an anti-clockwise torque. The same thing applies here. This one will be trying to turn the bar this side. So that's going to be an anti-clockwise torque. So this one is going to be a clockwise torque. This one is going to be an anti-clockwise torque. This one is going to be an anti-clockwise torque. So indicates with some saying that this bar is going to turn due to this weight force, this bar will turn in this direction. Due to this weight, the bar will turn in this direction, like that. Then due to this, the bar will turn in this direction. So this one will be clockwise torque. This one will be an anti-clockwise torque. This one will be an anti-clockwise torque. So we can work out, since we know the distances now, the distance from here to here, it's L minus x. The distance from here to there, it's x. The distance from here to there, it's x minus L over 2. We can work out what the torques are. That's what you've been asked to find. Of course, there's other things you can do. For example, Apart from that, when you try to apply, you can always apply first condition of equilibrium. So these forces are pointing down, the other force is pointing up. So if we choose up to be positive, then down to be negative, then you can apply the first condition of equilibrium and say the sum of the forces along the y direction equals to 0. So you're going to end up, if up is positive, then down is negative. So you're going to end up with FR plus minus 200 because it's pointing down, plus minus 100 because it's pointing down, plus minus 500 because it's pointing down also equals to 0. So you're going to end up with FR minus 200 minus 100 minus 500 equals to 0. So you're going to end up with FR equals to minus 800 neutron equals to 0. So you're going to end up with the reaction force being equals to 800 newtons. That's the first thing you can, that's the first useful piece of information you can get by applying the first condition of equilibrium. You can find out how much the reaction force is. The reaction force FRI is going to be the sum of these forces in the opposite direction, so that there is no acceleration. So there has to be a match. Are we clear? But that's not what this is not what we have been asked to find. But we need to find it because for us to work out the torques due to all these forces, we need to know the forces. FR we did not know how much it was. So if you're going to work out torque, we need to know how much it is. Are we clear?
Yes, sir. Yes, sir. Yeah.
So now that we know all the forces and their sizes, we can work out what for the 500 Newton force equals to 500. We're going to call that F2 500. So the torque in this particular case is going to be equals to F2, which is the 500 Newton force, times L minus X. The distance there, L minus X. So 500 newtons times L minus X. Here. So that's going to be the 500 here. Then put your 500 here. 500 newtons, L minus X. That's going to be sine 90, the angle between the direction in which the force is going and the distance from the pivot. That's going to be sine 90. So you're going to have these F2 L minus X. So in this particular case, if you want to expand, that's up to you, but I'll just put the 500 there anyway. So if you expand, you're going to end up having F2 L minus F2 X. You're going to have 500 newtons L minus 500 newtons X. So basically you just put your 500 here, 500 newtons. Then if you want to expand your thing, then you're going to end up with these. Are we clear?
Yes, sir.
Now there's for the weight 100 newtons. Then there's also a force F1 which is 200. Now for F1, there seems to be things which I don't understand what happened here. Oh, okay. So for the 500 one, we work out the 500 first, and we're calling it tau 1 because it's a clockwise torque. Okay? So we work it out separately and we call it tau 1 because it's the clockwise torque. Then for the other ones, they are anti-clockwise torques because they make the bar turn in the opposite direction. This one, the 100 makes the bar turn this way. The 200 makes the bar turn this way, which is an anti-clockwise direction. The distance for the 200 is x. The distance for the 100 is x minus 0.5 L. So in that particular case, we work out the second torque, the clockwise torques, the anti-clockwise torques. The clockwise torque is this one. This is clockwise. The anti-clockwise torques, we're calling them tau 2. That's going to be F1, which is the 200 times the distance x plus the weight times the distance x minus 0.5 L. So that's going to be your F1 is your 200 newtons. You put it there, multiplied by x plus your 100 newtons multiplied by x minus 0.5 L. So if you do your kind of expansion stuff, you're going to have 200 newtons X plus 100 newtons X minus 100 times 0.5, you're going to end up with 50 newtons L. So you're going to end up, this 200 Newton X plus 100 Newton X are going to end up with 300 Newton X minus 0.5 Newton L. So that's going to be your total anti-clockwise torque. Okay, now the steps are very clear. You identify which, according to the first condition of equilibrium, you identify which forces are pointing up, we identify which forces are pointing down, then you add them up, then you make sure that they're equals to 0. When you start applying the second condition of, why are we finding the torques? We're finding the torques because we want to apply the second condition of equilibrium. When we want to apply the second condition of equilibrium, then we need to find what are all the clockwise torques, what are all the anti-clockwise torques. Then after we do that, we add them and make sure that they're equals to 0. Okay, so in this particular case, so this bit here, tau 1, this is our clockwise torque. This 500 Newton L minus 500 Newton X. This bit which we have here, tau 2, this is our total anti-clockwise torques due to the two forces, the 200 Newton and also the 100 Newton. So, of course, if you add them, if you add the clockwise and anti-clockwise torques, them being equals to 0, it's also the same as doing this. You just say the clockwise torques must be equal to the anti-clockwise torques. If you don't want to do, if you have a choice, if you have a choice of saying clockwise can be positive or anti-clockwise can be negative. If clockwise is positive torques, then you make the anti-clockwise to be negative, or if you say anti-clockwise is positive, then the clockwise is going to be negative, or you can just say the clockwise torques have to be equal to the anti-clockwise torques like this. If you take this approach of just saying clockwise torques equal to the anti-clockwise torques, then your clockwise torques is this one, 500 Newton L minus 500 Newton X is equals to 300 Newton X minus 50 Newton L, like this. So this bit, this one, we can take to the other side. So you're going to end up with 300 Newton X plus 500. This lot here, we can take to the other side. So you're going to end up with 500 Newton L plus 50. So you're going to end up with 300 Newton X plus 500, then 500 Newton L plus 50 Newton L. So you're going to end up with 800 Newton X, and you're going to end up with 500 Newton L. So when you do that, so you're going to end up with X being equals to 500 Newton L divided by 800 Newton. So you're going to end up with X being equals to 0.69 L. So this is our value of X. Are we clear? So basically X is supposed to be 0.69 of L. So if your L, in this particular case, if your L, you say, okay, your L is 1 meter, then your X is going to be 0.69 times 1 meter. So you're going to end up with your X being equals to 0.68 meters. Okay.
Where did the 50 newtons come from?
The what?
50 newtons.
Where did the 50 newtons come from?
Yes.
This one?
Yeah, that's the one.
From here? From multiplying 100 times 0.5, we get 50.
Okay.
Okay, so you get your X equals to that much. So with your X equals to, now that you know how much your X is, you know the value of X, and if you assume to say L is equals to 100 meter, then you know the value of X, then you can go back and work out all these. So your first torque is going to be 200 times X. So here, you know how much X is now. So 200 times 0.69, that's how much? You get your torque. Then this bit here, you're going to have 100 times 0.69 minus 0.5 times 1. So you're going to get this torque. So you can find you can work out how much this torque is supposed to be. You can work out how much this torque is supposed to be. Similarly, you can also do the same thing here. 500 times L, 1. So 500 times 1, then minus 500 times 0.69. Then you're going to find out how much this torque is from your value of x and your value of 1, and L equals to 1. Is that clear?
Yes, sir.
Yeah. Any question?
Yes, sir. I have a question. I see a point where you say if our pipe is 1 meter.
Yeah. Because the length of the bar doesn't really matter. Whether it's 1 meter or it's 2 meters, you'll still be able to work out your x from there. So I just decided to say, okay, fine, let's just choose our length to be 1 meter.
Alright.
Yeah. Any other question? Okay, if there's no other question, then you make progress a bit. Here. Example number 10. Consider the situation shown in figure 10. The uniform 0.6 kilonewton beam is hinged at P. Find the tension in the tie rope and the components of the reaction forces exerted by the hinge on the beam. Give your answers to two significant figures. So, in this particular setup, we've got a couple of things. The first thing we have is, of course, is this beam here. This is the beam we are interested in. Okay. Then at the end of this beam, there is this weight, which is exerting a weight of 800 newtons. And as you can see, this point P here, where the hinge is, this has been marked as a pivot. So because it turns, our beam, if there was no other thing, if you're just pulling using this rope, it will turn about this particular point. So basically, this is our pivot here. Are we clear? Are we clear that this is our pivot?
Yes, sir. Yes, sir.
Okay. And I also hope people have people have their they are not printed out. Now, this weight is trying to pull this beam down. This weight, this side, this force, this side, is trying to pull. It's trying to do a couple of things. The first thing it's trying to do is it's trying to turn. If there was this rope was not there, it will try to turn this beam this way. Okay. Then of course, after the whole beam turns that way, the weight will still be there. So the next thing it will do, it will try to pull it down. So this weight is doing a couple of things. One, it's trying to turn the beam this way, and also it's trying to pull it down. Are we clear? Are we clear?
Yes, sir.
Yes, sir.
This weight is trying to turn the beam this side, and if this rope was not there, by the time the beam turns all the way up to this side, this same particular weight will try to pull the beam down. So it's doing two things: trying to pull the beam down, and also it's trying to turn it. This rope, if this weight was not there, this rope would try to turn the beam this way. Are we clear? It will try to turn the beam this way. this rope, because the rope is pulling in this particular direction. Okay, so there are also forces being exerted as this thing is trying to pull this way. The other thing is this rope, as it's pulling this beam, there's a part of it trying to turn the beam this way, but there's also a part of the rope here at this particular direction. There is a component of this tension, as we are going to work out. There's a component of this tension which is pulling the beam into the hinge. Are we clear? So there's a component of this, the X component. So you work out the X component of this thing, the tension. That's going to be your, whatever we're going to work out. But there's a part of this tension in this direction, which is pushing the beam into this hinge. So the hinge, as this beam is being pushed into the hinge is not going to just sit idle. The hinge will push back against the beam. Are we clear?
Yes.
So there are two things, there are certain things which are happening here to this particular hinge. Because of this tension in the rope, the hinge, the beam is being pushed back. The X component, because of the X component of this tension in the rope, the hinge, the beam is being pushed into the hinge this way. But the hinge is going to push back. So there is a part of this hinge, there is a force due to this hinge, which is pushing against the beam in this direction. That force is what we're going to call FH. The horizontal component, we're going to call it FRH. The horizontal component of the reaction, or you can just call it FH. There was either you call it FH or FRH, it doesn't really matter. It's the horizontal component of the reaction force of the reaction. So the reaction force is in this direction. It will push back against the beam. The beam is being pushed into the hinge. The hinge is pushing back. So you indicate that there's a force coming from this beam, from this pivot in this direction, which we're going to call FH. The other thing we mentioned is, of course, there is also a part of this tension which is trying to pull, apart from turning this beam upwards, there's also a part of this tension which is trying to pull the beam up. If there's a part of the thing trying to pull the beam up, so there's a component of this thing trying to pull the beam up, but the same thing is also happening by this. We've said that this bit will turn the beam like this way. If this thing was not there, then it will try to pull the beam down. So these forces, this one, the tension, the vertical component of the tension, the Y component of the tension, and the Y component of this weight, they are trying to pull this beam up or down. So there is a component of, as they are trying to pull this beam up or down, this, depending on where it happens, whether it's being pulled up, if it's being pulled up, if at the end of the day the beam feels like, apart from just being pushed into the hinge is pushing back against the beam, if at the end of the day it feels that the beam is being pulled up, then this particular thing is going to pull back against the beam, or if the beam is being pulled down, then it's going to pull up. So it doesn't really matter. So we just choose to fine. We are going to assume that in the Y component, this particular beam is probably being pushed up. Okay, so we need to have a component of the force exerted by the hinge or the beam horizontally. That's what we're calling FH. There is also a component of this force exerted vertically. We're going to call that FV. So the hinge, when you have a hinge, the hinge is pushing against the beam along the x-axis. We're calling that FH. The beam is also pushing against the beam, or pushing or pulling against the beam along the y-axis. You're going to call that HV. Are we clear?
Yes, sir.
Yeah. So when you do that, Which forces do we have? We have got this force. There's a force which lives in this rope. That's the tension. We're going to call that Ft. This particular tension, the pivot is here. The distance from the pivot to here, we know the distance. The distance is 3L divided by 4, which is just basically about 75% or something like that. 3 divided by 4 times L. So the distance is known up to this point. Then of course we know the angle which this force is making. So from this one, from the tension in this rope, we can work out what's going to be the torque. But at the moment, we don't know how much the tension in this rope is. Do we? I don't think so. We don't know how much the tension is. But we have been given the weight of the beam. Okay, so there's also the weight of the beam, which we have not been told. We have been given is 0.6, which is 600 newtons. There is also the weight of the beam. So the weight of the beam is going to act through the center here at L/2. So that somewhere here indicates weight of the beam, and the weight of the beam is going to act downwards here. So it's going to be at L/2. So down here, there has to be a weight of the beam somewhere here. That weight of the beam indicates on your printed diagram that the weight of the beam is acting downwards. And it has got 600 newtons. Then of course there is also this other guy here at a distance L, and the force is 800 newtons. So we have the forces acting on this particular beam is the tension in this rope. There is this guy down here. There is the weight of the bar, 600 newtons acting downwards at half the length. There is also the components of the reaction force acting horizontally, which we're going to call that FH. There is the other bit we're going to call FV. The exact direction of FV we don't know, so we're going to find out anyway. So that being the case, the first thing you do, I don't know why I didn't create a table, but you need to have a table, and the table was not created. Did I create a table or not? No, I didn't create a table, but we need to have a table. Okay. So I work out the x component of the tension. So that's going to be Ftx. Again, in this particular case, it depends what you choose to be your x-axis, positive x-axis. If you choose this side, so you'll be measuring your angle like that. If you choose that other side, then that's up to you. But whatever you choose, you stick to it. So if we choose this side to be, say we're going to be measuring the angle going this way like that, then that's fine. You stick to it. So in this particular case, you're going to have the x component. So you need a table where you're going to draw the tension. Then you work out the x component of the tension. The x component of the tension is going to be Ft cos 40 degrees. Then that's going to give you 0.77 Ft. So we need a table where you have vector, you have x component, y component. So this is the x component of the tension, 0.77 Ft. Then the y component of the tension is going to be Ft sine 40 degrees. You're going to have 0.64 that. Then, so that's with the tension. The other things you need are the weight. The weight is going to be pointing down. So if you're counting from this side, that's going to be all the way up to here. That's going to be 180. Then down here, you're going to have 270. So you work out your weight, the x component of the weight, the y component of the weight. So basically, you need a table for this, where you work out the x component of the weight, the y component of the weight, like the way you have been doing. Then same applies with this. You also work out the x component of this, the y component of this. But for the weight, it only has a y component. The same thing applies with this. The only thing which seems to have x and y components with this guy, the tension, there's an x component with a y component. Then this bit here, there's an x component, there's a y component there. So when you do that, if you add your forces along the x direction, you would end up having, I believe, you would end up having the following. You end up having this plus, now the negative here is, might explain my choice of, so basically I think what should happen here, we chose this, I started with this to be the x, positive x, but let's come this side. If we choose this side to be a positive x, then our angle up to here is going to be 180 minus 40, that's going to give us 140. So here, when you're working out this bit here, ftx, so it's going to be ft cos not 40, but you write 140. If you put, you start from this side. You start from this side. Say this is going to be a positive x-axis. Okay? If this end is going to be a positive x-axis, then the angle which this thing makes is going to be 140. Are we clear? Are we clear?
Yes, yes.
From this side. So you around this point, you do some xy plane. So you put this side to be your positive x-axis. This other side is going to be a negative x-axis. Up is going to be a positive y-axis. Down is going to be a negative y-axis. So all these forces, the tension, this weight 800, the 600, the weight pointing this direction, the one pointing up, all these we should put them in a table of components with your vector clearly indicated, with your y-axis and x-axis clearly indicated. So when you do that, so when you work out your x component in that case, so if the angle is, so in that case your ftx is going to be ft cos not 40, but you scratch out the 40, it's going to be ft cos 140 degrees. You're going to end up with 0.77. You're going to end up with, I think, minus 0.77. If I do that on my calculator, so cos 140, yeah, so you're going to end up with minus, so you put a minus here, minus 0.77 ft. Then when you work out the tension, you're going to have ft, fty, that's going to be ft sine 140, and that's going to be 0.64. So on your table which you're going to create, so for the vector ft, the x component is going to be minus 0.77 ft. The y component is going to be ft sine 140 degrees, which is going to give you 0.64 ft. I think we should do that. So you sketch a table somewhere, then we come to, we need, because we need to do things in a consistent way, we come to this guy here, which is the 800 Newton weight. If we are choosing this side to be our positive x-axis, then we go all the way like that here, that's going to be 180. Then we come this side here, that's going to be 270. So our x component is going to be, of this weight, is going to be 800, so 800 then times cos 270. So the x component is going to be 0, the x component of this. So you put on a table under vector 800, the x component of this is going to be 800 cos 270. That will give you a 0. Have we done that? Get a pencil somewhere and sketch. I'm doing the same this side. So for the tension, vector, so x component, then y component. So for the tension ft, my x component is minus 0.77 ft. My y component is just 0.64 ft. Then for this 800 Newton, so the x component is going to be 800 Newton cos 270. That's going to give you a 0. The y component is going to be 800 cos sine 270, sine 270, that's going to give you minus 800. Are we clear with that? Are we clear?
Yes, sir.
Then there is a weight of the bar. The weight of the bar is acting downwards through the center of the bar. Okay? So if the weight of the bar is acting downwards, again, if you're counting angles from this side, so all the way up to here, that's 180, then you need to indicate down this way, where the weight is acting, and it's 600. So the angle the weight of the bar makes is 270 also. So the weight of the bar, which is 600, so you under vector, you put 600, then under x component, you're going to write 600 newtons cos 270. That's going to give you a 0. Then under the y component, you write 600 sine 270. That's going to give you minus 600. Are we clear? So we have worked out the component for the tension, which is minus 0.77 ft for the x component, and for the y component is 0.64 ft. So basically what I'm trying to say here is we need a table of components which has not been put here. Okay, then for the 800, the x component turns out to be 800 newtons cos 270, that's your 0. Then your y component is 800 sine 270, that's your minus 800. Then for the 600, you have 600 cos 270, that's your 0, gives you a 0. Then for your y component, you get 600 sine 270, that gives you a 0. Then we have said there is also this other guy. There's the other guys, we have said FH, the horizontal component. So what you're saying here, FH is acting in this direction. The horizontal component is FH. We are assuming that FH is acting in this direction. If FH is acting in this direction, then we can work out under the vector column, you put FH there, then you can work out the x component of FH, which is going to be FH. Then if it's acting in that direction, the angle is going to be cos. So it's going to be cos 0 degrees. So that's going to give you just FH. Then on the y component, you're going to have FH sine 0 degrees, that's going to give you 0. So the FH, which is the component of the reaction force along the x-axis, only has got a y component. Then there's another one, FV. FV, we are assuming, we're going to make the assumption that FV is pointing up like this. So that's going to make it have an angle of 90 degrees. So you're going to have FV is equal to FV cos 90 degrees, that's going to give you 0. Then you're going to have FV sine 90 degrees, that's going to give you just FV. So your table of components should have the following. Under vector, there should be FT, there should be 800 Newton, there should be 600 Newtons, there should be FH, there should be FV. Then under the x components, for FT, your x component should be minus 0.77 FT, your y component must be 0.64 FT. Then under the 800, your x component should be 0, then your y component should be minus 800. Then under 600, your x component should be 0, your y component should be minus 600. Then under FH, your x component should be FH, your y component should be 0. Under FV, your x component should be 0, and your y component should be FV. Are we clear? Are we clear?
Yes, sir.
So with this table drawn, then you can simply add. You add the forces along the x-axis, your forces along the y-axis. So the sum of the forces along the x-axis. So along the x-axis, we have the only components, we have got FT which is minus 0.77, then plus 0 from the 800, plus 0 from the 600, then from the FH, then 0. So you're going to have minus 0.77 FT plus 0 plus 0 plus FH plus 0 equals to 0. When you add the forces along the x-axis and equate them, equals to 0. So when you do that, you're going to end up with FH minus 0.77 FT, which is equals to 0. And that's what we have down here. So the explanation could have been made better if we have a table of components, and that's what we have decided to do. So when you do this, when you do the addition here of the forces along the x-axis, so you end up with this. You end up with FH plus this BTA minus FTX, which is something which I've worked out already, which turns out to be this, minus 0.77 FT plus the other zeros. So you're going to end up with FH equals to 0.77 FT, which is what you have here. So you need to have a table. Always, you need to have a table of components which indicates which forces are acting on this particular beam and what are the components of these forces. Are we clear?
Yes, sir.
Then you add the forces along the y direction. So along the y direction, the sum of the forces along the y direction, from your table, you're going to see that you've got 0.64 Ft plus minus 800 newtons plus minus 600 newtons plus 0 plus Fv equals to 0. I hope you have that. So you're going to end up with 0.64 Ft minus 800 newtons minus 600 newtons plus Fv equals to that. So you end up with something which looks like 0.64 Ft minus this is 800, that I think that's 1400 newtons plus Fv equals to 0. Here, so you end up with this at the end of the day. So you end up with Fv plus 0.64 Ft is equals to 1400. So there are a couple of things here you need to notice. The first thing is we have got this equation here. The first equation you've come up with by adding the x components. In this equation you have come up with by adding the x components, there are two things you do not know. We don't know what FH is. We also don't know what FT is. So we've got two unknowns. The fact that you've got two unknowns means that you need to have two equations. Already, if you've got two unknowns, an equation where there are two things which are not known, it means that you need to come up with two equations. Okay? When you try to come up with the other equation, something funny happens. We end up having another unknown. So we end up having Fv plus Ft equals to this. So we end up having two equations with three unknowns. The unknowns are FH, Fv, and Ft. Is that clear? Are we clear? Is it clear to everyone that you have got two equations with three unknowns? FH, Ft, and Fv.
Yes, sir.
Now, if you have got two equations with three unknowns, mathematics rules demand that the number of unknowns should match the number of equations you have. So what we have here, we've got three unknowns with two equations. This is telling you that you need another equation so that you end up having three unknowns with three equations. So there's another equation which we need for us to be able to work out this whole problem. And that other equation which we need in this particular case, we are going to get it by working out, applying the second condition of equilibrium, the one which involves torque. Are we clear? So we're going to apply the second condition of equilibrium so that we can obtain our third equation. Now, when it comes to applying the second condition of equilibrium, I've always mentioned, a choice of pivot is very, very important. If you choose a good pivot is one. Of course, a pivot can be obvious, but a good pivot is one where multiple forces are passing through. In this particular case, our pivot here, there is a force FH acting in this direction. So our force FH acting in this direction passes through the pivot. There is other force FV acting upwards. It also passes through the pivot. So the forces FH and FV, which pass through the pivot, will not produce any torque. The only forces which are going to produce torque are this one, the one in the tension, the weight of the beam, and also this one. The tension is pulling the beam upwards. That is anti-clockwise. The weight of the beam is pushing the beam this side, which is clockwise. This one is pulling the beam this side, which is clockwise. So you've got this guy here producing an anti-clockwise torque. You've got the weight of the beam producing a clockwise torque. You've got this guy here producing clockwise torque. So we just work out, what is this much? What's the torque produced by this guy? It's going to be the distance, the force in this particular rope, which is Ft, times the distance which have been given, 3L divided by that, multiplied by the sine of the angle. That's going to give us a torque, which is the anti-clockwise torque. The other ones, the weight of the beam, which is 600, times the distance, which is half, 0.5 L, then times the angle, which is sine 90, is going to give us a torque here. Then this other side here is going to be the distance of the beam, which is L, times the weight of the beam, 800 times the angle, which is 90 degrees. So we can easily find the torques. So that's what you're going to do. So we're going to find our anti-clockwise torques and our clockwise torques. So our anti-clockwise torques and clockwise torques in this particular case, for the anti-clockwise torques, it's going to be this one. The anti-clockwise torque is going to be the tension in the rope multiplied by the distance from the pivot to the point where the force is acting, which is 3/4 L, then multiplied by the sine 40 degrees. So you're going to end up having Ft, then 0.75 L, then this much here, which is 64. They're going to end up having the tension in the rope, the torque being equals to 0.48 FTL. So this is going to be our torque due to the tension in the rope. Are we clear?
Yes, sir.
Then this is the anti-clockwise, because this force is turning the beam the other way. Okay, then we move on to the other forces which are going to turn the beam in a clockwise direction. That is the weight of the beam and also the other weight hanging on the other end. So the clockwise torques are due to two forces. So the clockwise torque tau T is going to be the weight of the beam acting at a distance of half the length, which is half of 1/5 L. Then the angle is at 90 plus the weight on the other end of the beam acting at the full length times at 90 degrees. So when you do that, you're going to end up having the second torque being equals to here 600 times 0.5 L plus 800 newtons times L. So you're going to end up have this 0.5 times this. That's going to give you 300 Newton L, then plus 800 Newton L. You're going to end up with 1100 Newton L. So this is going to be your clockwise torque or the clockwise torque. Now, for the beam not to rotate, the clockwise torques have to be equal to the anti-clockwise torques. So we equate the clockwise torques to the anti-clockwise torques. The clockwise is this one. This is the clockwise torques. So we put it this side. The anti-clockwise torques is what we just found up here. This one here. These are anti-clockwise torques found up there. Then we put it this other side, like this. Then when you do that, of course, now you can see there's L and L on both sides. So this L and L on both sides. So we can cancel out the L. So you're going to remain with 0.48 Ft equals to 1100 newtons. Then you divide by 0.48 on both sides. When you do that, you're going to end up with Ft being equals to 1100 newtons divided by 0.48. You're going to end up with Ft being equals to 2292 newtons. So this is how much tension is in the rope. Are we clear?
Yes.
Now, once we find out the tension, say the tension is this much, then we can come and put here. So we can find these other things. Here, you put here. So you can find your FV. It will be FV is equals to 0.64 times your 2000, whatever it is, equals to that. So you can work out your FV. You can also come and put here. Here, your FH is going to be equals to 0.44 multiplied by whatever your FT is. And that's what you're going to do. So when you do that, so you're going to have your FH. Your FH is equal to 0.77 FT. Your FT you found is this here, so you put it here. So you're going to end up with 0.77 times 2,292 newtons. So you're going to end up with FV equals to 1,765 newtons. Then your FV is going to be FV plus 0.64 FT. That's going equals to 1,400. That you substitute there. You're going to end up with FV being equals to this guy here. F equals to plus 146 that, then equals to this much here. Then you take it to the other side. You end up with F equals to 1,400 newtons minus 1,406 that. So you're going to end up with FV being equals to minus 67. So basically, this basically means that we assumed that our FV was pointing up, okay? But it turns out that our FV was not pointing up. In reality, it's actually pointing down. Hence the minus sign here. Are we clear? Are we clear?
Yes, sir.
Yeah. So this is a horizontal component of the reaction. This is a vertical component of the reaction. Now, I hope I did what I'm supposed to do. Then you can work out what is the reaction force. If you know the horizontal component, if you know the vertical component, the reaction force FR, so you can work out the reaction force. FR is going to be equal to the square root of FH squared plus FV squared. FR is equal to the square root, a big square root. Inside that square root, you put FH squared plus FR squared. Because these are components. What you have found are components. This is a component, X component. The other one is a Y component of the reaction force. Then you can use FR is equal to the square root of FH squared plus FV squared. Are we clear? So you can find out what the reaction force is going to be. In that, if we do that with what we have, so I'm going to have 1,000 for FH 1,765 squared plus, I open bracket, minus, down here, I'm going to have minus 67 squared. So I add them, then I take the square root of the solution. So I'm going to end up with FR being equals to 1,766 newtons. That's going to be my reaction force. 1,766 newtons. You can also find out what the angle it makes, since with a bar, what angle does the reaction make here? So the reaction, are we clear on how you find the reaction force? Are we clear on how you find the reaction force? Since you've got the X component of the reaction, this one, you've got the Y component of the reaction, this one. Therefore, the reaction force is going to be equal to the square root of this one squared plus this one squared. Are we clear? Yeah, like the way we used to do vectors, where you find the magnitude of a vector. You have got the X component of the vector, is this one. You have got the Y component of the vector, is this one. So you find the magnitude. Then after you find the magnitude, you can also find the angle which the reaction force makes. So we need to end here. Any questions? So the steps are really, the step which was missing in our in this particular thing was you creating a table of components where you have got the vector, the tension, the X components of the tension, the Y components of the tension, the other 800 Newton, you find out what's the X component, Y component, the 600, you find out what's the X component, Y component, the FH, you find the X component, Y component, then FV, you find the X component and Y component. then everything else will come out. So yeah, we stop here.
Sir,
Yes.
are the notes available on Moodle?
Yeah.
Okay.
The things are there. They're supposed to be printed. You print them so that you come and do things. Okay.
Alright, sir. Thank
Yeah.
you.
Any questions? Oh, so this one, basically what you're supposed to have is something like this. You can see from this table here. I have put everything. On this particular table, I have got everything. I've got the tension, I've got the weight, I've got all these things, the X components, the Y components, everything worked out properly. Basically, this is what you're supposed to do. This particular example is similar to what we are just from doing. If you look at this example, example number 11, almost the same stuff. Example number 11 is exactly similar to what we are supposed to do. So you just go through with what we know now. You go through this example unless there is any problem, but things should be very, very clear. That's the same. These are the same steps we have gone through with the other example. I'm trying to see what we can do and what we cannot do. Then here also things are in the, so example number 11, we're not going to do it. We'll not do it. So we'll have to end there. This one, let me, how did I do it? Okay, everything is also self-explanatory. Things are there unless you do not, unless you've got a problem somewhere, then you can let me know. But this whole thing of equilibrium needs to come to an end today. Other things there also, I think they are a bit, okay, so basically what we need to do, we can finish this equilibrium thing on Monday, because we need to finish it up. Okay, unless people, if we, so we ended with example, what we ended with the example. So this one, same logic. There is a hinge here, so there's going to be a reaction force, FV, FH, FV, the weight of the beam. There is a tension in this particular thing. So unless people have got a problem, we'll start with this one when we meet on Monday. But when on Monday we need to finish this thing. This whole thing needs to come to an end on Monday. Any questions?
No, sir.
Okay. Someone is just being admitted and the class is finished. Alright, so see you on Monday so that we close out this chapter, this whole thing on equilibrium. I'm sure by the time we reach somewhere there, it should be possible for you to answer almost any equilibrium question. Okay. So yeah, see you on Monday.